YouTube, this is Cooking Components again. Today I want to start cleaning the mainboard and the multi-IO card of the Peacock XT Turbo computer. So I'll start with the multi-IO card. And one of the first things to do will be to remove this battery. And then I'll try to preserve some of the stickers that are on the card. And when I've done that, I can start cleaning it up, trying to get rid of the battery fluids that have leaked all over the card and get rid of the corrosion, search for broken traces or damaged components and tidy that up. And the last step will be to replace the tantalum capacitors because they are prone to fail. And when they fail, they explode violently, and I don't want to have explosions inside of my computer. They should be in my game, not in my computer. Yeah, then let's get rid of the battery. Oh, that looked like dust flying off the battery when I snipped the terminal. And there was a battery flying off my multi-IO card. That's a poor little corroded bastard. I wish he didn't leak all over the multi-IO card and the mainboard. That's a lot to clean up. So I thought I might take a closer look at the battery, and I noticed that the heat shrink on the battery popped due to the corrosion needing more space around the battery. Yeah, I didn't expect that. But that's how the battery starts leaking. Yeah? Corrosion inside the battery needing more space, so it goes poof. And you can see the PCB-Traces embossed in the glue. And a little bit of corrosion. Why not? There's so much corrosion, I can't even make out where the battery is. But somewhere here there is the separation of the outer shell and the which is positive, and the battery negative pole, and somewhere here between there is the seal where the battery started leaking. Oh, that's awful. Okay, that doesn't look great. I don't know if you can see this very well, but the solder mask on the board, it looks like it bubbled up under the battery. Okay, let's take a closer look at the multi-IO card and its corrosion. Good so far. We are coming closer to the battery. You see the first corrosion. And now it's getting awful. Yeah, and there, I think the solder mask lifted from the PCB traces. Yeah, the solder that holds the clock crystal in place looks really degraded, so I think we need to get that off. Whoa, that's the ISO slot. And it looks fluffy. It looks like you could pet it. Okay. That's funny and awful at the same time. There's a lot to clean here. These are the serial pin headers, and you can see that they are corroded too. And then we have the... Where is it? Oh, there's a corroded jumper. And then we have the floppy connector, and you can see that these pins have some kind of corrosion on them too. Jumper 6 is corroded, and jumper 7 and 8 are corroded too. So this is the backside of the ISA connector, and yeah, it looks awful too. It looks like something is growing there. Now I'll try to remove all these stickers. I think the first one will be quite easy because I'll just try to get the IC out. Yeah, first sticker removed. And the other stickers will be removed using hot air, and I hope I don't destroy these stickers because I'm not sure if they are hot air safe. Okay, I'll turn up the heat a little. So I've been on 100 degrees C and now I'm at 130 degrees C. That worked good. Now I need something I can place this sticker on, and I think a plastic bag will do the trick. So I can remove the sticker easily later when I try to put it back on the card. Okay, that didn't work very well. Okay, on this sticker I have nothing to grab on. And now the other side. And now I think all the stickers are off. Yeah, looks good. And here are the rescued stickers. I hope we can get them back on the components when we are done cleaning. So there's a lot to clean on this board. I'll just start by covering everything in vinegar. And I've got a small little helper with me today. I hope it's not too noisy on the microphone. I think this toothbrush is broken. Perhaps the other one runs better. Oh, slightly. And now a water bath with a little bit of soap. So I'll rinse all the stuff off and come back to you later. There's nothing better to dry your freshly cleaned multi-IO card than a hot air station. So the card is now dry and clean. Let's make it dirty again. I've got here an old Corona mask. Some of these 100 low silicon something polishing tools. And an old kind of Dremel tool. And not to forget my fiberglass pen. So let's get started. So the mask is on. I'm ready now. Yeah, the copper is completely black. Nothing on the back side. But the front side looks a lot cleaner. So I'm just wiping it clean with a little bit of rubbing alcohol. This looks much better now. Let's take it under the microscope. So I think I removed most of the stop mask on the affected areas. Yeah, you might be able to see there are some traces close to vias that are heavily affected. But all in all, the copper still looks quite good. So I think I'll just add a little bit of solder and then coat the traces with fresh stop mask. I mean, there may be some vias that I have to treat with a little more attention. So perhaps I'll just drill them open and shove a wire through them to get both sides connected. Also, these traces look quite good. I mean, they are part of an unpopulated IC, and you might think, why fix them? Yeah, that's easy. Look on the other side of the board. Where are we? There are we. The traces go from the other side of the board all the way to other components. So, yeah, I think it's a good idea to fix them. By the way, this is our ISA slot. Yeah, I think there's a little bit of solder mask remaining and perhaps a little bit of corrosion, but all in all, this track looks good. So nothing to worry about. Yeah, and all the other traces look good too. And here's the other side of the ISA slot, and yeah, I didn't clean it up as well. So maybe I'll brush it a little bit too, but yeah, it doesn't look too bad. Oh, and there's still a little bit of green left. I think I should get that off. Oh, this pad has a heavy scratch. But it's only a scratch. I don't think that it's going through. So I'll try to clean that up a little more. Okay, you might be able to see that the first pin on the ISA slot, or the last pin, I don't know how they are. Oh, it's A31, so yeah, this one needs to be fixed. I'm not sure about the blackness on these pins, if it's only coating or if it's dirt. I think on this one it's only coating. So I'll try to get these battery terminals removed, and yeah, then I'll just coat everything with solder and hope for the best. But first, we need flux. No good solder connection without flux. And especially a lot of flux. And perhaps a little bit of fresh solder. So the first terminal was easy. I think that was not the leaky terminal of the battery, but the second one is giving me a fight. Perhaps I should try it from the other side. That could be easier. Yeah, and I just flanked the old solder out. That's a nasty connection. I think soldering to that will be a challenge too. This through-hole connection for the battery clearly disintegrated. But luckily, it seems to be one of the few spots that really disintegrated. Oh, sorry, I didn't take you with me. Yeah, I think this looks quite good. Time to clean it up and coat the new solder coated traces with new Soldermask. Yeah, this now looks really shiny. Beautiful. Oh, I missed something. I still need to tidy up the ISA connector connections. Okay, somehow the solder doesn't want to bridge that gap. Interesting. It looks like I'll need some small wires to bridge that gap. I'll take some out of this cable. Now I'll test all connections prior to coating them with a new solder mask. I can't see where this one is going, but at least it has connection to its trace. Where's my focus? There's my focus. Okay, this one isn't working. So there is a small break in this one connection. Let's just add a wire. It helps to turn on the soldering iron. Great, that one works now. So it looks like that this is only a two-sided board. So this connection here, which ends up inside this big copper trace, is going nowhere. So we don't need to care about it. What's up with this hole? Oh, there is no hole. I thought there was a hole. This is the other interesting hole. Yep, goes nowhere. So I'll just use my coating pen and coat all these connections again. Yeah, that looks quite good. So I'll leave this drying now and think about a solution to replace the battery. After the new solder mask has dried, I want to take a closer look at the circuit for the battery. And first of all, I looked at the specifications of the 8-bit ISA slot. This is the 16-bit one, but we just have to take a look at the first section of the ISA slot, and it's the same. So there are these two pins, B31, which is ground, and B29, which is 5 volts. So I could find them on the other side of the board. They go directly to this capacitor on this side. So it's easy to measure the 5-volt rail from here. Here is the ground connection of the ISA slot. And this goes directly to the ground connection of the battery. And here we have the 5-volt connection. And this goes to this diode up here. It's D3. So for me, the important part now was to find out how the NiCad battery got charged and how the NiCad battery is connected to the real-time clock. So I'm measuring from the positive terminal of the battery to the resistor R18. The resistor R18 has 220 ohm and it's used to charge the battery. When the computer is turned off, then the real-time clock needs only a couple microamps, and then the resistor of 220 ohm is negligible. It does nothing at that low current. So from the resistor 18, we have a connection to the diode D3. And the diode D3 is connected to our positive rail. So as long as the computer is turned on, the battery is charged using the diode and the resistor. And after that, when the computer is turned off, the diode blocks the current flow to the 5-volt rail, which is now ground. And then the current can flow from resistor 18 to pin 24 of U19, which is the real-time clock. The only other two connected components are these two capacitors, C27 and C33, which is a 4.4 nanofarad capacitor, and C27 is a 10 microfarad capacitor. So I'll try to doodle this circuit down for you. We have the ground connection, which goes to the battery, which has around 3 to 3.6 volts. Connected to that, we have the resistor R18 with 220 ohms. After that, we have a diode which is connected to 5 volts. And from this intermediate connection, we have the two capacitors in parallel. And then we have our RTC pin 24, which is called U19. And the only thing I'll do now is replace this resistor with a diode. So only the battery can feed the circuit, but not the 5 volts can feed the battery. For this purpose, I've selected an 1N4148 diode, which is a small signal diode, and it has a reverse current of, I think, 25 nanoamps. And that's important because I don't want to charge the battery while the computer is running, or the battery will go poof. The only other thing to solder is these capacitors, which are all old tantalum capacitors, and they might fail and explode violently, so I want to replace them. That's why I'm going to write them all down. So these two, this one here. I'm not sure how big this one is. Oh, it's the same. Sometimes when they dip them in plastic, they look a little bit funny and you think, oh, that's perhaps a higher value, but it's the same capacitor. So they are all 10 microfarads, 16 volts. The only two different tantalum capacitors are here. And they are also 10 microfarads, but I think they are higher value of voltage, but there's nothing written on them where I can find something out about them. So let's assume they are 25 volts. Maybe. So I'll try to find suitable replacements. And for all your Telefunken fanboys, yeah, this is it. This is the Telefunken, what is it? 1N4 148 diode, which I found in my parts drawer. And yeah, this could be a really old diode. I don't know if they are still making them. Beautiful. So I've got here the data sheet of the real-time clock. And for us interesting are the voltages, which are the output enabled voltage from 4 volts to 5.5 volts, and the power down voltage, which is 2 volts to 5.5 volts. So if the computer is turned off, the real-time clock is set into power down mode, and in that mode it works with only 2 volts. So if we connect a 3.2 volt button cell battery and we have our diode in place for protecting the battery from being charged when the computer is turned on, we have a voltage of 3.2 to 3.0 volts minus 0.6 volts for the diode, which should be 2.4 volts to 2.6 volts, rough estimate. And that should be enough to run our real-time clock. And here is the current drawer in the data sheet, and they prepared an interesting difference. They define the current for the static and the current for the dynamic behavior. And for the dynamic behavior when you use the I/O, so when the real-time clock is fully powered on. And they state that when you use a frequency of DC, so when you don't have a clock crystal connected, you only need 10 microamps, but when you use a normal configuration with a clock crystal, you need 20 microamps. And 20 microamps is quite a lot. I simply calculated this as a rough estimate using 225 milliamps for a standard CR2032 button cell. And at 20 microamps, we get a runtime of 11,250 hours, which means 468 days and a little bit. And this is just 1.28 years. And in that calculation, we don't have any other losses. We don't have the diode drop, and especially we don't have the charging diode, which will still be in place and which can leak a little bit of current from the battery to the 5-volt rail while the computer's turned off. And that are losses we have to calculate too, but I don't know which diode this is, and I don't care. Just to give you a rough estimate, we are lucky when we hit a year of battery runtime, and that's the reason why they used a NiCad battery and not a primary cell, like a button cell. By the way, this is the datasheet of our beautiful Telefunken diode that we want to use instead of R18. And yeah, it has 57 volt blocking current. It has a voltage drop of 0.62 to 0.72 volts at 5 milliamps, and with the current that our real-time clock uses, we are far beyond that, so the voltage drop might even be lower. And this is important from my perspective, we have a reverse blocking current at 20 volts of only 25 nanoamps. And again, we are at only 5 volts, or to be exactly, we are at around 1.8 volts when our battery has 3.2 volts and our voltage rail has 5 volts. So our reverse blocking current will be even less. So I don't see any problem with this, that the button cell might be overcharged. So I'll try to desolder R18 and all the tantalum capacitors now, and after that I'll replace the tantalum capacitors with some other capacitors I've got here, and I'll replace R18 with the diode. I think the solder is a little bit corroded. I'll be using these beautiful 10 microfarad 25 volts polymer capacitors, which I bought on DigiKey a while ago. And here I've got a battery holder that might fit this spot nicely. Beautiful. There's still a mess to clean away, and after that we can start reapplying the stickers. So the last step to do now is reapplying the stickers, and I think the first one is quite easy because we don't need any adhesive for this. Done. Okay, I think this one isn't sticking anymore. Oh, okay. Yeah. But it's not really great. Yeah, it's not sticking. So, perhaps this one will help. I hope this will try and keep it in position, but I'm not sure. Okay, where did this one belong? Somewhere here. Well, I don't care. Beautiful. So I think we are done with the multi-IO card. It looks very good, very promising, and yeah, think this might be working again. The only two things that are missing are these two jumpers. Beautiful. Next up, the mainboard. I've got a new perspective on the mainboard for you, so you can see all the glorious corrosion. Okay, it's not glorious, it's just awful. But yeah, there's a lot of it. And there's non-corrosion on the ISA slots. Only a little bit of foam. And oh, what's that? Okay, that's a lot of corrosion. And then none again. And then for the fungi lovers of you, there's even a little bit of mold. And then a little bit of dust. Oh, there's the CPU. Nice. So I'll remove the stickers again, or the components that have stickers on them and can be removed, and then we can start cleaning. And there's a little sticker on the board. It looks very moldy, and I think that's dropped off from the battery. Oh, it's completely disintegrating, so I will happily throw that away. And there's the funny little piece of foam. And it's gone. I think this is the last sticker on the main board. So I just thought it might be a good idea to remove the memory ICs before I proceed with the acid. So when I remove these ICs with my tool, I just go under the back of the IC and lift it slightly. And then I shove the tool as far to the front of the IC as I can. and I push on the back of the IC so this cannot come out of the socket, and I try to lift the front. Easy. Yeah, and I think I'll get the CPU out too. Perhaps on this one I'll just try to go from the other side too and not put so much force on the CPU itself. There's not a lot of room to get to the other side of the CPU. It's out. And no bent pins. Nice. I don't have a big piece of ESD foam, so the CPU and memory will rest in these ESD boxes while we are cleaning the mainboard. And some of these memory ICs just said, oh, let's start to make love, not war, and they started hugging. Neutralizing the alkaline blood from the battery looks funny and sounds funny, but believe me, it doesn't smell funny. It just smells after vinegar, and I think there's some chemical reactions, and you really shouldn't breathe this. Oh, it starts bubbling a little bit. And smelling. Okay, enough of this. Crazy. I don't know how long I need to let this going, but there's still a little bit of fizzling happening. I don't know how long it takes the vinegar to dissolve away the copper, so rinsing it off with water might be a good idea. I rinsed the board a little bit to get the rest of the vinegar off, and now a bath in more water to get the rest of the vinegar off, and yeah, a little bit of soap. And let's start with the mechanical part of the cleaning.
Hey, keep going.
It looks like some of the battery acid came through here where the mounting hole is. So there are some contacts that look a little bit darker, but it doesn't look like an issue. I think we need here a brush for big boys. So I applied the big boy brush only to the really nasty looking contacts like the ISA slot and some of the IC sockets. And they are still looking bad. After cleaning the board with soap, water and the brush, I rinsed it off in the shower and used compressed air to blow the water out from all the small cavities. And then I dried the board. So it looks nice and shiny now, but I think on some corners of the board we still need to look a little bit closer. I'm starting now on the bottom right corner of the main board. There's the first row of memory that was not populated, and these sockets look okay so far, but when we go north a little bit, it gets a little bit green, and okay, maybe I should replace that socket, but it's not used, so I don't want to do the effort, but yeah. There are also some 0 ohm resistors where I rubbed the marking off accidentally, and the legs are a little bit corroded and the traces are a little bit corroded. Yeah, I think we need to check that if these connections are still working. Yeah, the legs of these components look a little bit corroded, but at least we took away all the battery fluids, so this shouldn't be corroding any further. Okay, now we go to the second row of memories. These were populated and these sockets look quite good. Yeah, I think we can leave that. Yeah, they look good. Third row of memory. Oh, yeah, it starts right at the corner of the board. And this looks good so far. Yeah, perhaps a little bit of residue. And here's the empty ROM socket. And here's the ROM socket that was populated with the ROM chip with the big blue sticker on it. So that's so far for the memory and ROM section. And then there was one ISA slot. That's the last ISA slot. That looks okay. Yeah, these two, and I think this one was the corroded ISA slot. Yeah, you can still see a little bit of green left, but it looks quite good. For how green it was, it looks really good. Maybe a little bit on this corner, but I think you don't need to use a specific ISA slot for your card, so maybe I'll just populate one of the other ISA slots. That should be an easy solution. Because hey, this one is looking very nice. And the other ones too. So maybe there are some corroded traces next to it. Yeah, perhaps a little bit of corrosion on the solder itself. Yeah, but I don't see any issue. So we are good in this corner. Nice. And there was a suspicious corner on the backside of the board where the battery fluids leaked through a mounting hole, but I mean, perhaps these solder points are a little bit tarnished. They are not as shiny as these ones, clearly, but they don't look bad either. Yeah, so I think we are good on the backside. Nice. So maybe I should decide to get this socket out because the trace back here doesn't look so good, even if it's still working, which I didn't measure, but I should measure these traces. And it also looks dark down here. Yeah. And there's a wire that looks quite dark. Maybe I need to desolder these sockets. At least the first two. Oh. And this trace looks quite dark. That I should check too. And it's desoldering time. Let me inspect these solder joints. Okay, this one wiggles. I'm not sure with this one. Oh. So with a little bit of luck, they'll just come out. And yeah, this socket seems to be loose. Nice. One out, one to go. Something is still not loose enough with this socket. Yep. That's it. Okay, that's a microscope job. Please, YouTube, next time I decide to lift IC sockets for searching for more corrosion, please just stop me. This doesn't look really good. I mean, it's not too heavy, but it's ugly as hell. And it's in a position where I can't really work on it, so I hope I can show you the process a little bit, but if not, yeah, you'll see the finished result. Okay, I'll just try to clean it up a little bit so we can get a better look. Okay, there's at least a little bit that has been eaten away. I'm sorry, but I don't have a better camera angle for this job. At least where I can see what I'm doing. And there's never too much flux. Yeah, I just filled all the holes where the legs of the IC sockets should go through. That was certainly a good idea. Looks nice. So, cleaning up. Then a fresh new coat of Soldermask. And we can put these sockets back in. So the two new sockets are soldered in. I won't replace the other sockets at the moment, even if I really don't like how they look, especially when you see the new shiny ones. But I want to test this board first. Before testing this board, I want to remove all these tantalum capacitors and replace them with other capacitors, because old tantalum capacitors are prone to fail, and when they fail, they do this violently and burn up. I just took a look over the board and counted all the capacitors and tried to find out what kind of capacitors these are. So there are 3 tantalum capacitors with a capacity of 10 microfarads and a voltage of 25 volts. So they are most probably on the 12 volt and the negative 12 volt line. And there are 16 4.7 microfarad capacitors that have a voltage of 16 volts, and they are on the 5 volt lines and perhaps 1 or 2 on the negative 5 volt line. And I found 2 bags of capacitors to replace them. One is 4.7 microfarad 50 volts and one is 10 microfarad 25 volts. So these match up exactly in terms of capacity and voltage. These have a higher voltage rating. That's not an issue. They would replace fine. But there's one key difference. These are aluminum electrolytic capacitors and these are aluminum polymer capacitors. And these capacitors have a very low internal resistance. These have a standard internal resistance, and all the capacitors on the board are tantalum capacitors and they have a especially low internal resistance. So we need low internal resistance on this board, and all these capacitors are used for smoothing the voltage. They are not used for something where the capacitance is especially critical, but the internal resistance is critical. So I'll not use these capacitors, even if these are very good capacitors. I'll use these ones, even if they are bigger, but hey, the voltage is enough. Or it's even enough for the 12 volt rail, so that's good. The capacitance is a little bit higher. That's not an issue. But they have a low internal resistance, and that is what we need to replace tantalum capacitors. So I think I'll just start desoldering all the tantalum capacitors. It's about to get noisy. So I think the rest needs to be done with more manual soldering, because on most of these capacitors, the short legs are very short. So you have a little bit of a challenge when you want to wiggle the pin around in the solder hole and desoldering it. So yeah, on this one it works, but I think on most of these small capacitors the legs will be still attached a little bit to the hole. So I'll clean this up manually. So when you replace capacitors, you always have to be really careful, because when you look on these tantalum capacitors, they have their positive lead marked. But when you look on a random electrolytic capacitor, they have their negative lead marked. So don't screw that up. And if you look on this brand new out of the package one, you see a marking, but that doesn't really tell you if it is a positive or negative marking. But you also have the leads. And oh, wait a moment. When you get them fresh out of the box, they have a longer and a shorter lead. And the shorter is the one that's also marked. It's the negative lead, and the longer lead is always the positive lead. So if you are not sure, search for the data sheet. So I'll just solder in all the new capacitors. Yeah, so I think this looks quite nice. All new caps. Beautiful. And now checking all the memory ICs for corrosion. Ah, this one is good. A little bit of corrosion. Much better. Okay, maybe I will just clean the outside edges and not the inside edges. At least if it's only a little bit of corrosion or dirt. Because I'm too lazy. Oh yeah, this one. Ah, that was the one from the bad socket, I think. And now finally to the CPU. I mean, it's clean because it was not close to the battery acid or the corrosion, but there's something I want to show you about the CPU. How often in your life did you see an AMD CPU with an Intel copyright on it? I just noticed this. I've never seen this before. An old AMD CPU and an Intel copyright on it. Nice. And now I think it's time to put all the ICs back onto the main board. Okay, so the thermal imaging camera is ready. Am I recording? Now I'm recording. So yeah, let's give it a try. Oh yeah, on the pose analyzer card, component is getting hot. That's not good. Oh yeah, the CPU is getting hot to 50 degrees C. But that could be normal, but it's rising fast. I don't like that. Yeah, post analyzer card is hot too. All other chips are getting warm. Some more than others. Yeah, I hear nothing, I see nothing. Perhaps without the post analyzer card. I don't know if this is compatible. I mean, it was correctly inserted. By the way, is the keyboard doing something? Nope, nothing. Yeah, CPU is getting warm. I don't know what to do about this. At least the CPU is inserted correctly into the socket. I mean, it doesn't feel really warm. I mean, perhaps this chip isn't seated correctly. Nah, no, that's good. I don't see if I missed something. So let's try again. Yeah, you can see the CPU getting hot. And some other components. Perhaps I should add the multi-IO card. I mean, it could be needed by something because it contains the battery and the RTC. So let me just get a battery for that. So there's a multi-IO card, there's a battery. Let me just combine these two items. Nice, that one fits. Even it's only in 2025. Okay, I didn't know that I had one of them. So multi-IO card somewhere here. Okay, it's in the way. Perhaps better here. No, there's... will it collide with the capacitor? Go in! Yeah, a little bit. So my capacitors are too high. Oh man. I'll just bend it a little bit out of the way. It's still colliding. Oh man, okay. You need to look out for your capacitors, I think. Okay, let's try again. Let me see the multi-IO card. So yeah, chips are getting warm. But still nothing. Okay, I think this will be getting a very long project. Oh, it's now at 64 degrees. But it's not really feeling hot. So I poked around on the internet for a while, and I found out that on such old mainboards you can mostly, not completely, but mostly forget about your post-analyzer cards, because if these mainboards do create post messages, or however you want to call it, they do it on a different address as these cards are reading out. So these, for the most of it, don't work on XT computers, but there are some helpful LEDs. So there are LEDs for the power and for some status signals, and yeah, that helped me to figure out a little bit, but I think I'll come to that part later. The first thing I did was I just took my oscilloscope probe, and with the board powered on, I started poking around a little bit. So when you look at the signals of the CPU, well, they are a little bit quick, but you can see 4.7 something megahertz. That's the CPU clock, so that's okay. I need to scale out a little bit. And here are all the address lines and so on. Yeah, I know there's one address line behaving a little bit weird, but that's only a couple of seconds after start. So if I reset the CPU, there is something going on the signal, which looks strange. Let me stop that. Yeah, some deep normal looking waveforms and some not normal looking waveforms. I don't know what to do about this or what to think about this. Yeah, I don't care at the moment. So clearly something is happening on the CPU side. Clock is there. I measured the crystal frequencies. They're all good. And I even found out where the beeper signal goes, but there's nothing happening. So there are no beep tones generated. So maybe it's an XT thing. Maybe it's a thing of this mainboard or of its configuration. I really don't know. But then I took a look at the LEDs of the post analyzer card. Let me just turn it off. So when you look on the LEDs, let me get it closer. There are some things written on the LEDs. So there's a reset LED, frame, IRD epsilon, and clock. I don't know what these are all about, but I mean, reset is clear, and IDR is something regarding interrupts on the bus. So if there is an interrupt, I think the LED goes on, and if the interrupt is handled by the CPU, so the CPU cares about it and turns the interrupt back off, then the LED goes off. So this means if this LED is doing something, then the CPU will be doing something. So let me turn it on. And you see reset, okay. Oh, and reset goes off and IDR is doing something. So there's clearly something happening on the system. So yeah. And then I thought, yeah, okay, maybe I should just try to connect something to the graphics card. And then I things exploded in a way that I tried to find some kind of adapter to adapt the signal to a VGA monitor, and then find a VGA monitor that actually accepts the vertical frequency of this graphics card, but I had no luck. I tried also a VGA to HDMI adapters, which I didn't have any luck with, and yeah, I even adapted my RetroThink, but no, nothing there. So yeah, and I thought, yeah, I need to get this at least somehow visualized, and yeah, then I came to the conclusion that I might just connect my oscilloscope to the signals. Oh, I lost the cable. To the signals and try to find out what is happening there. I mean, it's a monochrome display, so we should only see signal where lines are drawn. Okay, I mean, I can't give you a real picture on the oscilloscope screen, but I can try to find out at least if something's happening on the screen, and yeah, that would be yeah, at least a step forward, and I could try to find something later to connect to it, but I would at least know if something's working. And I mean, if you can initialize your graphics card and put something on the screen, there's at least life in the system. So yeah, I hope I connected the correct signals. Let me find it all for you, or I will just rewire it. I had it working before, so I hope it will work now. Okay. Yeah, that looks good. So you see the yellow trace, that's the, what is it? The horizontal sync. So that's the refreshing of the whole screen. If I zoom out more, you can even see the frequency. It's around 50 Hertz. Good. The clock signal is around 18 kilohertz. So that's an old standard. I don't know how I should say it. It's just an old standard. So yeah. And yeah, I think most interesting would be, you see, yeah, something's happening there still on the screen. Let me just restart the system. And what you see on the blue line is the vertical sync signal. So we are stopping a full frame. And then, no, it's not a vertical sync signal. I think what I connected is the luminance, or just the picture signal, how I should call it. I mean, it's a black and white, so you would only see ones and zeros for where a pixel should be bright and where not. So you see the horizontal sync. So one big yellow trace is exactly one picture on the screen, and the blue traces are pixels, and groups are like lines on the screen. So you can see at least lines appear that are a little bit intermittent, but yeah, it's trying to draw text, and sometimes there are pixels and sometimes there are no pixels. So that's it so far. Yeah, let me try it. So it starts up, reset is low, reset is high. Oh, vice versa, and you see it's like a blinking cursor there. And I don't know if there will still be something happening, but all of it just happened. So yeah, it just went done with that line and then went to the next line on the screen, and there's something blinking. So I would expect there's an error message blinking. I don't know, but it looks like it's working. Or it's at least doing something. So I think that's so far as I can go today. I'll finish this video up on this point, and yeah, something else appeared on the screen. Nice. So yeah, I think that's all for today. Thank you for watching. Have a nice day. Please give the video a thumbs up. Like, share, comment, subscribe, all the good stuff. Thank you for watching, and see you in my next video. Bye. And reset. It's nice to see that at least something is happening. Beautiful. And now a little bit of bonus content for all the weirdos that are still watching. I got myself an MDA to HDMI adapter that's using a Raspberry Pi and some small custom PCB to convert our MDA signal to HDMI. Let me plug this in. So the Raspberry Pi should now be booting. And I think we get a picture on the screen. Beautiful. The adapter's booted. So yeah, I'll just turn on the power supply and hope nothing is burning up. Oh, and something's happening. And yeah, you can see the computer is booting. It's a little bit faint on the display, but yeah, that's due to the excessive light here on this workbench. And we have no keyboard connected, so yeah, I can't do anything with it. But it's booting, at least, or not booting, but at least it just showed the BIOS version, showed that there's no keyboard connected, and it checked the memory. So beautiful. I would declare this as a win, and I'll see you in my next video when we are trying to fix this computer. Bye. Oh, it's so cute. Oh, it's taking a long time for only 512 kilobytes. It's old, it's slow, it has a small CPU. And that were other times back then.